Okay, so chapter 6, part 1. So chapter 6 is about matrices and linear and nonlinear systems. For most people, this is kind of a breath of fresh air after the challenge of chapter 5. But that's not to say it's easy. It's still pre-calculated. So multivariable linear systems and row operations. Sorry. Multivariable linear systems and row operations. Let's break down that title because that's a little confusing. I saw some of you squinting at it, probably because some of those words are hard to understand. Multivariable just means more than one variable. Linear means nothing is squared or cubed. It's all to the first power. Systems mean more than one equation that is true for the same variables at the same time. And then row operations. This is new, probably, depending on how in-depth John Jones went into matrices. But it's a way to, you know when you type RREF in your calculator? This row operations are what's going on in the background. It's the mechanism the calculator uses to solve the system. So I'm going to teach you the by-hand way once. It's tedious. After that, we'll use the calculator. But 6 years. Question, sir? Mr. Pearson. Yeah, Jeff is usually extremely thorough. To a fault, actually. Like myself. Share a lot of characteristics. So we're going to solve systems of linear equations using matrices and Gaussian elimination. Solve systems of linear equations using matrices and Gauss-Jordan elimination. I don't differentiate between those two. I think that's not necessary. So multivariable linear system. So as I said, this is more than one linear equation. A multivariable linear system is more than one equation. Now, row echelon form, that is when you have a matrix that has ones on the main diagonal and zeros below, but not necessarily above. So REF, not RREF, that's a different animal. We'll get to that in a second. But you have ones on the main diagonal and zeros below. That is row echelon form. Gaussian elimination is a method to solve systems. We'll discuss. Augmented matrix. So this is when you add one matrix to another, and it's usually indicated with a dotted line at the point where the matrices are merged. So that's an example of what an augmented matrix might look like. Coefficient matrix. So this is when you take a system and rewrite it as a matrix. So if I've got 2x plus y equals 5 and x minus y equals 3, the coefficient matrix will be 2, 1 on the first row and 1, -1 on the second row. So it's when you take a system and convert its coefficients into a matrix. We often augment that with the solution matrix and then run RREF on it. That's the method you were probably taught to solve systems with more than 2 variables. You got 3, RREF is your only practical mechanism because the algebraic methods take so very long. All right, reduced row echelon form. So this is a little bit of a different animal than REF. In reduced row echelon form, you've got ones on the main diagonal, zeros everywhere else. But it's important to note that there could be elements out here. So it could have elements out there, but the main diagonal and the elements above and below are ones and zeros respectively. Oh, it's on full screen. Too much. Start of the virtual college fair week at EHS. Please encourage interested students to attend sessions beginning at 3 p.m. this evening and extending through Thursday evening. So I'll show this to you guys real quick. This is something Mr. Duncan and Alex Campbell have been working on. So today is Tusculum, Walter State, Lincoln Memorial University, King University, and UT at Chattanooga. Tomorrow, Appalachian State, Carson Newman, East Tennessee State, and Tennessee Tech. So if you're interested in attending any of those colleges, the admissions personnel will be present on the Zoom meeting to be able to talk to them about the process. Can always help and never hurt to know those people. Okay, so let's go to some examples here. So a matrix is an array of values listed in rows and columns. So in this particular case, I've got 2 rows and 3 columns. So the rows are horizontal, and then the columns are vertical. And each individual item in the rows and columns are called elements. So we have 6 total elements in this matrix, 2 rows, 3 columns. And it's typically named with a capital letter. Just convention. There's no special reason for this. It's just what somebody did one time and everybody followed suit thereafter. So usually you use a capital letter to stand in for a matrix as a variable. And the elements can be anything. They could be non-real. They could be algebraic. It could be whatever. Typically they're just numbers at the pre-calculus level. But they could be other things. Now, to name a certain element, we use a double subscript. Did I get you straight, Jesse?
She said she didn't know what happened, that she could make this something.
Yeah, I know what happened. They screwed up. Wow, I don't know. So if I name a specific element, I will do so with a double subscript. The first item in the subscript is the row. The second is the column. So for example, let's say I wanted the element in the second row, third column. And that's actually negative I. So second row, third column is negative I. See what I mean here? So the subscript, the variable that we've used to stand for the matrix, and then the double subscript we'll call an individual element. A11, so that's first row, first column, is 2. A21, second row, first column, 4. You guys get the idea there. So this is just some variable and naming convention for matrices that you've probably seen before. But I'm going to bet it's been a while, at the very least. And you may well have forgotten it. All right, moving on. So you don't want all this stuff just yet. Wow. Okay, so first of all, writing it in triangular form using Gaussian elimination. So first of all, let's write it in as a matrix. So we're going to create an augmented coefficient matrix that matches this system. So we're going to use equation 1 for the first row, equation 2 for the second, equation 3 for the third. We're going to use the first variable for the first column, the second for the second column, the third variable for the third column, and then the number that they're equal to for the augmented solution column. So the variables are as follows: 1, 3, 2, are the coefficients for the variables, rather. 3, 1, 2, 2, negative 2, 3, 5, 7, 3. So this part is the coefficient matrix. This part is the solution matrix. And we've squashed them together, augmented them together in this way. All right, so you guys have for a very long time been taking this and punching it into your calculator, hitting RREF, and there's your solution. I'm going to show you, I'm going to allow you a little peek behind the curtain and show you what's actually going on there. So as I said, I'll show you once the algebraic way. Okay, so first of all, do you notice this x has 1 for its coefficient? So that's important to us. It makes our life kind of easy, because I can rewrite this first equation as follows. If I subtract 3y and 2z from each side, I get this expression that's equal to x. And so what we'll do is plug both of these, plug that in for both of the other x's, and then simplify the result. So this is going to go in here and here. First of all, in the second equation. So this is 3 times negative 3y minus 2z plus 5 plus y minus 2z equals 7. So if I simplify this mess, I get negative 9y minus 6z plus 15 plus y minus 2z equals 7. So let's combine our like terms here. Minus 9y and plus y are minus 8y. Minus 6z and minus 2z are minus 8z. And then I've got 15 over here and 7 over here. So if I subtract this 15 away, I get negative 8. So I can divide through by negative 8, and I get y plus z equals 1. Notice the x part is gone. So I now have just two variables. Man, I must have wrote that fast. Small over here. Now we'll do the third equation. So that is 2 times negative 3y minus 2z plus 5 plus 2y plus 3z equals 3. Distribute here, negative 6y minus 4z plus 10 plus 2y plus 3z equals 3. Combine our like terms. Minus 6y and plus 2y is minus 4y. Minus 4z and plus 3z is minus z. Yes. And then if I subtract 10 from each side, I get negative 7. For the sake of eliminating negatives, because it's so easy to do it, we'll multiply through by negative 1. Get this. So now we can rewrite our system using the same first equation. So I'll just copy that. X plus 3y plus 2z equals 5. This second equation, y plus z equals 1, and then 4y plus z equals 7. So that's our first step in moving to what's called triangular form, which is analogous to REF in a matrix. So we're algebraically moving this into REF. We've got one more step to do so. I need to consider the y. I need to eliminate the y down here to make it into that triangular format. Do you guys see? So if I eliminate the y here, I need to use this. So I've got y equals 1 minus z from this second equation. So I'm going to take this expression and plug it in for y here. So this is 4 times 1 minus z, and it gets easier as you go here, plus z equals 7. 4 minus 4z plus z equals 7. So 4 minus 3z equals 7. Subtract 4, and I get negative 3z equals 3, and z equals negative 1. Now we're ready to write our system in a fully triangular format. Let's do that over here in blue. So I've got the same first equation. Second equation is y plus z equals 1. And the last equation is z equals negative 1. Now, do you see how the coefficient part of this forms a little right triangle? So that is triangle form. And in the form of a matrix, that's analogous to REF, row echelon form. You see how the coefficients are 1 along the main diagonal and nothing is below them? So that's analogous to REF. From here, the system is trivial to solve. So I've got Z already. So if Z is -1, I just plug that in to the equation above it, and I get Y plus -1 equals 1. So add 1 to each side, and Y equals 2. And now I plug both of these into the first equation, and I get X plus 3 times 2 plus 2 times -1 equals 5. So X plus 6 minus 2 equals 5. X plus 4 equals 5. X equals 1. So you're just setting yourself up for this easy solution when you get to REF. No problem, buddy. So what we could write the system as now is X plus 0Y plus 0Z equals 1. And then 0x plus y plus 0z equals 2. And 0x plus 0y plus z equals -1. Now, do you see how this is analogous once we've solved it to REF? 1's on the main diagonal, 0's both above and below. So this is what's going on in the background when we hit the REF button. This algebra. You can also describe it with row operations. Let's see here. Do this the calculator way, just to refresh your memory on that. So if you go to your home screen on your calculator and hit Matrix, it brings up this screen. And we navigate over to the Edit tab and hit Enter on the first matrix A. It's going to ask us what dimensions do we want. Do you see how for this situation, we need 3 rows and then 4 columns? And then we populate those with the appropriate values. 1, 3, 2, 5 is our first row. 3, 1, -2, and 7 is our second row. 2, 2, 3, 3 is our third row. And now just a little error parsing that's going to save you some grief, because it's really easy to hit the wrong button. Go down, if you put them in horizontally, which is the default, check them vertically. 5, 7, 3, 2, -2, 3, 3, 1, 2. And then 1, 3, 2. Okay, we're good. Now we're going to use the matrix button again from the home screen. Go to the math portion and navigate all the way down to option B, I believe. REF. Then matrix button yet again. Hit enter to call the matrix you just defined. And then enter again to run REF on it. And we see the solution.
Can you run the one at a time on the, like, how to get the matrix in there?
Yeah, so matrix, edit, choose whichever matrix. Now, sometimes you're defining multiple matrices. Let's say I've got a problem where I've got an A and a B. I would navigate up or down to the appropriate one. We're using A this time. And then we define the dimensions, 3 by 4 in this case, and then we define the individual elements. Once you've done that, you can quit to the home screen, and it's stored in memory.
Yeah, I couldn't figure out how to get you go to names instead of like edit.
Yes, to call the matrix, you use names. To define the matrix, you use edit.
Okay.
So edit first time only, after that names. So the center tab is the math operations, and all the way down at option B is RREF. Really going to be beneficial for you guys to run through this on your own calculators because everyone is a little different. Oh yeah, you're still having the battery issue. Yeah, it could be that little clock battery. You know, the one that's in behind the. Well, remind me one day when we're not doing something and I'll try to fix it.
Okay. Because it'll work, like whenever I first put batteries in.
Well, you have to clear the whole memory. So I wouldn't bother. I would just, you could redefine it whenever you need to. Okay, so just to recap, we took a matrix or a system and rewrote it as a matrix. And you guys have for a very long time been hitting RREF and solving it. Here I showed you the mechanism for that. First of all, to get to REF, and then the algebraic mechanism to get to RREF. So you know what's going on in the background when you hit that button on your calculator. Okay, so your calculator uses row operations. So row operations work like this. And this is just analogous exactly to the algebra you just saw me do. The first type of row operation is I can add or subtract any row to or from any other. So these are the row operations. I can add or subtract any row to or from any other in a matrix that is representative of the system. The second rule is I can multiply any row by a constant. And that constant can be a fraction, so that effectively gives us division as well. See, I can multiply by 1/8. And that's analogous to dividing by 8, for example. And then 3 is kind of a cheesy one. I can do 1 and 2 together at the same time. So the row operations for matrices are that. We can add or subtract any row to or from any other, multiply any row by a constant. We can do both of those things together. And going through another problem with row operations is probably worthwhile, just so you know what the heck I'm talking about when I say that. So we'll solve this one instead of algebraically. We'll do the row operations, which again are analogous. So let's convert this to a system, or to a matrix that represents the system. Colby, what should my first row be? So I agree with this 1 and 1, but I don't agree with the 2.
Negative.
There you go. See, that mistake would have thrown off your solution, as tiny as it was. And then we have the value that it's equal to out here. So, Rachel, tell me what the second row should be.
2, 3, 1.
Excellent. And then Bristol, tell me what the third row should be. Very good. So we're going to attack this And have you ever seen those puzzles? They're kind of a thing of the past, but they're square and they're missing one tile. And you can manipulate all the others around and move the missing tile around, and the goal is to complete the picture. So this is sort of like that. If you go in the wrong order, you will undo the work you have already done. You know, there's a certain pattern you have to approach those with, and that's true as well here. And that pattern starts with this element. So we want to do the first column. We want to create a situation where we have zeros, a 1 here. So we make that happen with multiplication, if necessary. It's not here because it's already 1. This is our first target, the upper left, but it's already what we want it to be. So we move on to our second target, which is second row, first column. And we're going to change this to a 0. Do you see how I can do that? By taking row 2 and subtracting away 2 times row 1. That will create a 0 here. So row 2, and you have to remember your matrix operations here. So we're going to turn row 2 into its own little matrix for the purposes of this. So row 2, subtracting away 2 times row 1, using the third rule for row operations, or the third thing we can do. So this is 2, -3, 1, 3, minus. And to multiply a matrix by a scalar, we just multiply all the elements by that scalar. It's very intuitive. Matrices in general are very intuitive. Their strength. And to subtract a matrix from another, you just subtract the corresponding elements. So this is 2 minus 2 is 0. -3 minus a -4 is 1. -3 minus a -4 is 1. 1 minus 2 is -1. And 3 minus 6 is -3. So I'm going to take row 2 and replace it with our new and improved row 2. Get our original here. And I'll just make him a infinite clone. It's going to be hard to keep up with me if I do it that way. So remind me to go slow if you get behind. All right, so we're getting rid of the original row 2 and replacing it with our new and improved row 2. And the task of having a 0 here is complete. So now we have a 0 below that 1. So upper left, 1, first goal, already was the case. So second goal was to get a 0 here. Third goal, get a 0 here. So you're going to get the elements on the main diagonal to be 1, get everything below them to be 0. That's your first goal. So in this case, I want to take row 3 and subtract away row 1. So I've got 1, -2, 2, 5, and I'm going to subtract away 1, -2, 1, 3. So the corresponding elements here, 1 minus 1 is 0. -2 minus a -2 is 0. That's a bonus right there. 2 minus 1 is -1. I'm sorry, positive 1. 2 minus 1, positive 1. 5 minus 3, 2. So once again, we're going to replace the previous row with our new and improved row. That's not going to be very helpful. Basically, I have to rewrite the whole thing. So the middle row is now 0, 1, -1, -3. last row is now 0, 0, 1, 2. Now we kind of got lucky. There were two cases where we got 2 for the price of 1, and that was by design, I'm sure. But do you see how now we are in row echelon form? Not row reduced echelon form, but we're in row echelon form. So once we're in row echelon form, our new targets in order are the values above the main diagonal from left to right. So the way I'm going to attack that -2 is I'm going to take row sub 1 and I'm going to add 2 times row sub 2. See how that's going to make this a 0? Because 2 times 1 is 2, 2 plus -2 is 0. So I've got 1, -2, 1, 3, plus 2 times 0, 1, -1, -3. 1, -2, 1, 3, plus 0, 2, -2, -6. And these are tedious, the by hand way. This is to make you appreciate what the calculator does for you in this respect. This is among the most tedious of all algebraic tasks, to solve a system of more than 2 equations. System of 4 equations, man. That would even bog down the calculator. Okay, so 1 plus 0 is 1. -2 plus 2 is 0. There's what we wanted. We wanted that to be a 0. And then 1 plus -2 is -1. And then 3 plus -6 is -3. So I'll copy this bad boy. Not what I wanted to do. Undo. Yeah, there we go. Copy. There we go. So we'll replace the first row now with the new and improved first row. So 0, -1, -3. Everybody with me so far? And we have gotten that 0 to match. Now we need to get rid of this -1 in the first row, third column. So the way we're going to do that is use row 3. You see how once we have 1s all through here, the rest of it is real trivial. So we're going to take R1 and we're going to replace it with R1 plus R3. So I can add any row to or from any other. I can multiply any row by a constant. I can do both of those simultaneously. Here we're using just row 1. So 1, 0, -1, -3, plus R3, 0, 0, 1, 2. So this is 1 plus 0, 0, 0 plus 0 is 0, -1 plus 1 is 0. And then -3 plus 2 is -1. We'll replace our previous first row with this. We're almost there, guys. One more value. So the only offender left is here, this -1. So we're going to take row 2. We're going to add something to it. What should I add to it, Jesse? Exactly. that's going to be 0, 1, -1, -3, plus 0, 0, 1, 2. So you get 0, 1, 0, -1. And now we will be in our final form. So, -1, -1. 1's on the main diagonal, 0's everywhere else, and the values our variables are equal to on that rightmost column. If that's right. One's on the main diagonal, 0's above and below, and these values over here are equal to our variables. So x equals -1, y equals -1, z equals 2. And we can come back here to the, that's too big to even fit, even with the entire page function. So I'll do, no, there's no real way to do it. Well, I could, but it would be not visible. So just going back to this, -1, -1, and 2. Let's see if it works. So -1 minus 2 times -1. So that's -1 minus a -2. So that's 1 plus 2 equals 3. That works. And usually you want to test it in 2 of the 3 equations just to be sure. So if I go down here, this is also going to be +1 plus 2 times 2 is 4. 1 plus 4 is 5. Yes. So our solution works. You, of course, can also plug this in the calculator. So let's do that real quick, just to get you some good practice. So we go to the matrix button, go over to edit, and this matrix dimensions are already right. We need only change the elements. Make sure you can do this, because once you are away from me, you're on your own. I expect you to be able to operate your calculator. I'm just double checking my elements here, which is tedious. I'm not a double checker by nature. I've come to trust one thing in the universe, and that's my own competency. So I don't double check myself typically, but in this case you should. It's just too easy to hit the wrong button or make something negative or whatever. So we quit out of this to the home screen, hit the matrix button again, go to math, navigate down to option B, and then matrix yet again, call the one we defined, hit enter. We'll see only the final product. Those intermediate steps, of course, the calculator doesn't show, but it's going through them in the background to get to you. All right, once again, just to recap, we have solved the system algebraically, and I showed you how that was analogous to the triangle setup, or REF, and to RREF at the very end. Then I went through the actual row operations of the matrix themselves and showed you also how REF and RREF can be arrived at by manual means. In other words, doing it yourself. From this point forward, we'll rely on the calculator to do those things for us. Questions about either of those? All right, cool. So just writing an augmented matrix. Sometimes this can be a challenge. And if you'll notice here, look carefully and tell me how many variables we have, Rowdy. Yes, there's a W, X, Y, and Z. How many people would mindlessly have written 1, 1, -1, 5, and so on? Most people would have. So in this case, they throw that little curveball at you. Of having the W, X, Y, Z. and then the number that they're equal to. So what is the W's coefficient in the first equation?
W, it would be 0.
Very good. And then we got 1, 1, -1, 5. And then tell me what the second row would be, Grace.
2, 3, 0.
And then what at the very end? Good. She didn't get fooled. Riley, what about the third one? So I agree with this, but you're missing something there. You have the 0 for the Z, and that's the kind of boo-boo that can mess up the whole works. We did not have a task after this for this problem. Just creating the augmented matrix was our task. All right. So here's one for you guys. Take just a minute or so and write me an augmented coefficient matrix for this. Somebody goes to the bathroom at the same time every day. I always think something's afoot. Dual gang. Illicit boyfriend meet. Nothing's happening. All right, Holden, tell me what to write in the first row.
I have 1, 2, 0, 1, 2.
Excellent. What about the second row, column?
Second row, 0, 1, 1, -1.
Excellent. Third row, Colton.
2, -3, 1, 2, -2.
Last row, Rachel.
1, 0,
Good.
3, -1.
You're right so far. Say again.
Did I miss up on something?
You just didn't give me the last value. Yeah, you guys are frequently leaving this off. This is part of the augmented matrix, so don't leave off this part. This is the coefficient matrix. This is part of the matrix you need to solve the system, so don't leave that last element off. Okay, so that's it. One thing to be cautious of, before the end of the chapter, they're going to throw one at you that's not standard form. In other words, variables won't be alpha times. You'll have to use the commutative property of addition to rearrange them. In this case, they are. Okay, elementary row operations. I've already talked about this. Row echelon form is when you have ones on the main diagonal, zeros below. Notice now there'll be a test question. Is this matrix in row echelon form? I want you to notice full 0 rows below do not change the fact that it's still in row echelon form. So as long as it's got ones on the main diagonal and zeros below, we're good to go. And the stuff over here does not impact its ability.
So is the main diagonal always going to be?
No, it's however many, do you see how this is augmented? So this is what it's saying is in row echelon form. And it's the main diagonal from one edge to the other. So if it gives, it'll have those dotted lines. So those dotted lines indicate this is extra crap we squished on here. Not to be considered for the RREF status. That can be really confusing. I'm going to go over some examples when I do the study.
And I have another question. Any like the variables that are up there that are above the ones, can those be zeros as well? Like one or
They can be.
one, two?
They can be, but they don't have to be an REF. So REF is different than RREF.
Right.
In REF, they can be, but they don't have to be. Good question. Other questions? All right. So is this one in REF? What do you think, Allie? Say again? Okay, what makes you think it's disqualified? Okay, so here's just a little mental algorithm for you to go through. Are there ones on the main diagonal? Are there zeros below? Then the answer is yes.
So even if there's only 1 0?
Yeah.
Then, okay.
Because it's a 2 by 2, and then we squashed on a 2 by 1 here at the end. But it's a 2 by 2, meaning there'll only be the one element below it. All right, good job. Part B. What about this one, Rowdy?
No.
No, look at this main diagonal. That's not ones. We're offset there, so that doesn't cut it. Cannot have that offset status. This is a no. What about this one, Mackenzie? Yeah, this is a tricky one. This is the kind of one they throw at you on the test, and it can confuse you. But a whole row of zeros below doesn't change anything. Still in REF. So this is a yes. So of the 4 you see here, Riley, which is not in row echelon form? D is in delta. Does everybody see why? So that's the exact kind of thing you're going to see on that test. So you're going to have a quiz over the first 2 sections on Wednesday, and then you're going to have a test on Saturday. So I'm going to deliver all the lessons by the end of the day on Friday, giving you a test. Now, if I'm not mistaken, guys, I think I had it due by the end of the day on Sunday. And my thinking was I didn't want to interfere with your fall break. So I wanted everything to be done before your fall break begins. And that's really for your own good. Because I know there will be those of you that will have a tendency to think, I've got a whole week, F this, I'm not taking that. And then guess what? You're going to forget half of what you learned, and by the end of the week, you will not be prepared at all for the test. And what was really a very easy test will become very challenging.
Wait, so this weekend there's one?
Yes.
Okay.
Yeah, and the reason why I'm doing that is so you can have an unimpeded fall break.
So next week is our fall break?
Yes. You're off all week next week. And a week is a long time to forget mathematics. You will struggle with the test if you put it off. And in general, pay attention to my due dates. Now, I think some of you guys had the impression in the spring that due dates were just absolutely negotiable. You know, just do it when you feel like it, if you feel like it. And the teacher was somewhat delighted that you even bothered to turn it in. So that was the spring. Now, you've slowly come to realize that that's not going to cut it in the fall, I hope. And some of you are still trying to use that spring approach. It absolutely will not work. And I'm going to have to be stricter with late work going forward because I just can't keep up with it. So it's cumulative. You know, every lesson I give, there's still a few stragglers that want to turn that stuff in. So I've had to totally cut off the first 9 weeks, as we discussed. And going forward, I'm going to give you a pretty harsh penalty, 30 points for work that's more than 3 days late. If it's less than 3 days late, I'll give you 1 question's worth of points per day off, which is typically 10. So 1 day late minus 10, 2 days late minus 20, 3 or more minus 30. So point there is get your stuff in. Alan.
I know this is, last problem will ask, do you know where we can find the information for the college? Like what colleges are
Just
today?
got an email about it, so it
Should be on your Gmail, your student Gmail.
Is it through like under your own?
I got it from Ruby.
I would have thought, I thought Dusty Duncan, that's who sent it to me, but maybe Joe Diaz for some reason sent it to the students. Anyway, it should be in your student Gmail, the thing about the college fair. And it's very important. You know, over the course of your life, a college can be worth millions of dollars. So it's definitely worth pursuing. And sometimes kids say, well, you know, I just want to go to work and not worry about school anymore. Well, you're going to put yourself in a position of poverty, probably. Because in today's day and age, an unskilled laborer is not going to do very well. So you should do something. Pay attention, Colin. It's important. Okay, restaurants. 3 families ordered meals of hamburgers, french fries, and drinks. The items they ordered and their total bills are shown below. Write and solve a system of equations to determine the cost of each item. So you've got the Tao family, the Jenkins family, and the Hernandez family. Hamburgers, fries, and drinks. The Tao family, they ain't playing around. They ordered 6 hamburgers. And then 5 fries and 5 drinks. You know what that tells me? Dad ordered 2. I'm not dad, by the way. And their total was $55. Jenkins, 2 hamburgers, 1 fry, 1 drink. Is that just one dude? $15. 1, 3, and 2 for the Hernandez family. So we want to solve this and know the cost of each item. So let's let the hamburgers be X, French fries be Y, the drinks be Z, and this total, of course, would be the number that they sum to. So we can create an augmented coefficient matrix from this information. We go to matrix, edit, 3 by 4. The dimensions are already correct. I'm going to say 6, 5, 5, 55, 2, 1, 1, 15, and 1, 3, 2, 18. So 621, 513, 512, 55, 15, 18. All right, once we have it defined, we'll quit to the home screen, hit matrix once again, go to math, all the way down to option B, and then matrix again. Select the matrix we defined, hit enter, and it tells me the hamburger is $5, French fry is $3, and the drink is $2. So 5, 3, 2. Five, 3, 2. Questions about this? As I said, moving forward, we're going to use the calculator. You don't have to sit through another one of those extensive algebraic solutions. It is good to see once because it makes you appreciate that calculator when you hit that RREF button. Look how much work it's saving. And you know who's really saving you all that work is the person that programmed that software. So whoever that coder was back in the 80s. Thanks, bros. All right. So here's one for you guys. You've got a movie theater that sells 3 kinds of tickets: senior citizens, adults, and children. The table shows the number of each kind of ticket purchased by 3 different families. Write and solve the system of equations to determine the cost of each ticket. So tell me how much an old person costs, a regular age person, and then a kid. Man, this question is super dated. Because who goes to the movies anymore? Every time I go, it's like me and 2 old people.
Right.
Honestly, that's a thing.
I kind of like it though.
I think these are cheap tickets for, well, they're half decent price tickets for.
Oh yeah, but honestly, I kind of like it with less people on there.
Yeah, it's cool.
The only time I've seen the movies packed recently is like a brand new movie that
Like the
everyone's
first
excited
day
for.
it came out.
Yeah, the Endgame. When I went and saw Endgame, the theater was back.
So whenever I got like a release night Star Wars tickets for the recent Star Wars, and it was packed. But after
Yeah,
that,
that was a good
after that I
movie.
went again because my half brother wanted to see it, and there was like 2 people in it, and that was like 3 days later.
You know, I'm just kind of scarred from the prequels, to be honest. This series was pretty good, and the ending was good. I liked it. But the prequels just like
The third prequel is the only good
What?
prequel.
No, the prequels are the best.
Anakin is such a detestable character.
What about Obi-Wan?
Obi-Wan is like I don't know.
Best character
I don't-
out of all the Star Wars.
I love Obi-Wan from the prequels, but Anakin just runs the place.
That's true.
But what about Rey? Rey had nothing.
It was hard at first to buy into her being a Jedi, but later on.
The only good thing about the first prequel is, now that's moderate. That's literally the only good thing
No,
about
the
the
first
first
prequel doesn't matter.
Exactly. The only good prequel is the third one.
I don't like them.
I like them all, but the first one's tough.
All right. See, who have I not called on here today? I think I've gotten everybody almost. Macy, what is the solution here? 5, 7, and 4. So you can take grandma and the kiddo to the movie and total $16. That's pretty good. Pretty cheap date.
That popcorn about 14 times.
Yeah, after you get the popcorn and the slushy and the candy bar, yeah, it's going to be 3 times that.
Yes.
I don't know if you guys, I don't know if you guys go to the one at the Pinnacle in Bristol.
Yeah.
My wife likes to go there. They've got a package. It's like 2 popcorns and 2 candies and a drink for $28. Not kidding, it's that much. Okay, guys. So solving a system, I think we're squared away on this. I don't really feel like you need to do another one of those. But there are certain types of systems we have to be cautious about. And the calculator can give us a confusing output in these cases. So there are 3 possibilities. So when I talk about, these are 3 linear equations, right? These are 3 lines in space. So when we graph space, we need a z-axis. So, and it's usually graphed like this. You guys see how that could represent a 3-dimensional space? I'm asking you to stretch your brains a little bit. So this is X and Y. We've taken the XY plane and laid it flat, and then the Z-axis comes up out of it. Okay, anyway, don't worry too much about this. But the way space works, 3 lines. They can intersect in one spot like this. They can overlap like that and have an infinite number of solutions. Or they can never touch all 3 together at all. So what this means is you can have one solution, you can have no solution, or you can have infinite solutions. So those are the 3 possibilities when we deal with these 3 variable systems. You've seen this. You've seen what this looks like on your calculator. What the no solution looks like is the calculator will give you a contradiction. So it'll tell you something that is impossible. And that usually comes in this form. So you'll have a final row that is all zeros and then a constant. So what this is telling you is 0 is equal to 3. Not possible. So it's a contradiction, meaning the system has no solutions. And then over here, this is going to give you an identity. Let me scoop this over so I'm not confusing you guys. So an identity looks like this. So that final row, we're told that 0 equals 0. Well, that's always true. And so we know this is an infinite solution situation. So let's punch this one in our calculator and see if we encounter one of those unusual cases. So if I go, gosh, 10 minutes left. Time flies when you're having fun. So putting this in 1, 2, 1, 8, 2, 3, -1, 13, 1, 1, -2, 5. So which one of those special cases is this? Infinite solutions. So this is a case where the lines are overlapping in space, and there's infinite points where they have a solution to all three. So that means we could algebraically modify these equations and make them all be the same thing. Fun fact. All right. So if I plug this one in, which I'll do real quick. I'll do it over here where I can type a little faster. So that's 2, 3, -1, 1, 1, 1, -2, 5, 1, 2, 1, 8. So, which one of the special cases do we see here? Indeed, it's a contradiction, telling us that 0 equals 1. So this is no solution. And the previous one, which I never really wrote it on here, but was infinite solutions. Okay. So any questions about anything we've learned? In that case, I will call our lesson to a halt and give you a brief assignment. All right, guys, so here's your lesson. Page 372, or your homework for the lesson. Page 372, 2, 4, 8, 14, and 15. And follow the instructions. There'll be cases where it asks you to work it out. And again, doing it one time is worthwhile.